All right, welcome to Introduction to Meteorology, Lecture 6 from Chapter 6 of your book on air pressure and winds. And in this chapter, we're going to talk about atmospheric pressure and the means by which we measure atmospheric pressure. And what does it mean when you have high pressure in one place and low pressure in another? And what is the effect of that pressure difference? We're going to begin to talk about not just surface charts, but also upper air charts when we discuss why the wind blows and upper level winds and surface winds, and our means by which we measure and determine the wind. So this is a very important chapter in understanding the circulations within the atmosphere.
The first thing we want to talk about is how we actually measure air pressure. Air pressure, or atmospheric pressure, is measured by the force exerted by air molecules over a given area. As that weight is pulled by gravity toward the surface, it creates pressure over the surface, and that's our air pressure. So standard atmospheric pressure at the surface, generally around 1,000 millibars. To be precise, standard atmospheric pressure is 1,013.25 millibars, which equals 29.92 inches of mercury. So where did we get that inches of mercury concept? From the original barometers, as you can see here. Essentially a capillary tube, a very thin tube, a vacuum tube, turned upside down in a dish of mercury, quicksilver, which flows like a liquid. As the air pressure pushes down on the dish of mercury, it pushes the mercury up the capillary tube, and we say the pressure is rising. And standard atmospheric pressure was typically measured at that 29.92 inches of mercury. Now, as there's less air pressure and lower pressure in the atmosphere, well, then that mercury falls. And so we say the barometer is falling. As air pressure increases, that mercury rises, and we say the barometer is rising. On the right, we have some typical air pressures. We'll start at the bottom with 870 millibars being the lowest recorded sea level pressure in Typhoon Tip back in 1979. 882 millibars, Hurricane Wilma in 2005. Katrina was down around 920 millibars, that is. An area we consider a deep area of low pressure over the continent, about 980 millibars. There's your standard sea level pressure. 1040 would be a very high pressure system, and then some of the highest air pressure recorded, the highest being over Mongolia with 1,085 millibars. So what is air pressure really? We've talked about air pressure being the mass of all the molecules in the column of air above your head, whether you're at the surface or halfway up the atmosphere or all the way at the top of the atmosphere. So our conceptual model shows a city with a column of air over the city, and every one of those gray dots is an air molecule. And we'll just assume that our atmospheric pressure is 1,000 millibars, and so we'll say there's 1,000 of those dots. That is the pressure, the weight of the air at the surface creating air pressure at the surface. So air pressure is the mass of air above any given level, quite literally the weight of the atmosphere above us. And as you can see, as we go up the column of air, well, at the very surface, we've got 1,000 of those air molecules above us. If you go up to the top of the buildings, say we only have about 750 of those air molecules. If you go about halfway up the column, then there's only about 500 of those air molecules. And of course, as you get to the top, there's no air molecules, and that would be the edge of space. Now, this is just a conceptual model where the molecules are not crowded at the surface due to gravity. In the real world, of course, the real atmosphere, pressure decreases rapidly at first because gravity pulls the molecules toward the surface, and then pressure decreases more slowly with height. Knowing that air pressure decreases with height, it would make sense that over a landmass with varying topography, higher elevations and lower elevations, you'd have varied air pressure readings. And here we have 4 stations, A, B, C, and D, and they all have different air pressure readings because at the surface, down by the beach, it's about 1,000 millibars. That makes sense. As we say, surface pressure about 1,000 millibars. As you go up that mountain, air pressure drops about 894, and that all makes sense. But the surface weather maps that we look at, we don't adjust for height. As a matter of fact, when you think of the surface weather map, the surface analysis that we've looked at, it's all flat. There's no topography. On a surface weather map, we make an adjustment for the height, for the elevation. So station pressure is the barometric reading corrected for temperature, gravity, and instrument error. So every station, whether it's A, B, C, or D, Melbourne, Tampa, Saskatchewan, wherever it is, every station has temperature variations, gravity variations, and instrument error. The station pressure that's recorded at that station, for instance, at station B, 979 millibars, that's the station pressure. Sea level pressure is station pressure observations corrected for altitude, and the correction's pretty straightforward, 10 millibars for every 100 meters. And so in each of these situations, we are going to add millibars for the height above the surface, 600 meters, 300 meters, 1100 meters. And then what we get on that flat sea level pressure chart at the very bottom is station readings of station A being 1,012 millibars. That's corrected for altitude. Station B being 1,009 millibars. Station C 1,004, and station D 1,000 millibars. So the reality is where it looks like the lowest pressure on the topographic map at the top is station C at 894. When it's corrected for altitude, we see the lowest pressure is in fact D at the beach with 1,000 millibars and higher pressure at A. And so there's a pressure gradient from A to D. That's the direction the wind would blow, from west to east. Now, isobars, as we've said, are lines connecting points of equal pressure, always in millibars on surface charts and typically at 4 millibar increments. So a sea level pressure chart is a surface weather map. We know that we can measure the air pressure at the surface, and we see that on a surface weather map. But we also know as we travel up in elevation, up the column of air, you can measure pressure at every point as well. You're just measuring the number of molecules, the weight of the air above you. And what we find out is in different temperatures of air, those air columns act differently. And it's no real surprise that a colder column of air is going to contract and not be as high as a warmer column of air. So at the bottom, we see City 1 and City 2 at the same pressure. The surface pressure is the same. And also, the air columns are about the same height. If we chill the air column over City 1 and warm the air column over City 2, well, the air column over City 1 contracts and the air column over City 2 expands, and something changes now with not only the surface pressure but the upper level pressure. So in the conversation of air pressure and temperature, it takes a shorter column of cold, more dense air to exert the same surface pressure as a taller column of warm, less dense air. And we see that in that center illustration. Atmospheric pressure decreases more rapidly in the cold column. So what I'm saying is, at the surface in City 1, in the center illustration, the atmospheric pressure is 1,000 millibars. If I go halfway up the column to the top of those buildings, we would say the atmospheric pressure is 500 millibars. And at the very top of that air column, your atmospheric pressure is 0 millibars. If you compare that with the warm column in City 2, atmospheric pressure at the surface, the same, 1,000 millibars. But if you go to the top of the buildings, there's about 3/4 of the air molecules above you. So it's about 750 millibars. So at the same level in the cold column, that's 500 millibars. That same level in the warm column is 750 millibars. So at that level, in the upper levels, the pressure is literally higher. And we see that illustrated on the far right, where there is higher pressure at the same level. And you can count. There are simply more molecules of air above the H at the very same level as above the L. Count above the L, 2, 4, 6, 8, 10, 12 molecules, where above the H, it's significantly higher. There's higher pressure in the upper levels above the city with warm air than the city with cool air. Because there's a pressure gradient, air is pushed from high pressure to low pressure, and that is that air movement in the upper levels. So warm air aloft is usually associated with high atmospheric pressure aloft, and cold air aloft is associated with low atmospheric pressure aloft. And the horizontal difference in temperature creates a horizontal difference in pressure that causes air to move from high to low pressure along the pressure gradient force. How does that pressure gradient in the upper levels of the atmosphere that we see here again in our illustration with high pressure at the same level in the upper levels as in the warm column as low pressure at the same level in the cool column? That creates a pressure gradient where wind is blowing from the high to low. How does that create surface wind? Well, the pressure gradient force causes the air aloft to move from high pressure to low pressure. As the air leaves the column above city 2, so now we're looking at city 2, as those air molecules move from the H over to the low, there are fewer molecules above the surface, and the pressure at the surface decreases. Simply, there's less mass above the surface. As air accumulates over city 1, the surface pressure increases. There's literally more mass above the surface. So what does this look like? That pressure gradient force quite literally takes molecules in city 2 around the H and moves them over toward city 1. So there's fewer molecules above the surface, which means lower pressure at the surface, in city 2. And in city 1, there's more molecules above the surface, which means higher pressure over city 1. And literally, you create the opposite pressure gradient force at the surface. And with the pressure gradient from high to low, therefore the wind at the surface blows in the opposite direction. Higher pressure at the surface over city 1 causes the air to move from city 1 to city 2, where the surface pressure is lower and the circulation is created and the wind blows. And that would be a convection cell. This is an animation describing that direct thermal circulation. So what you're going to need to do is click the play button there in the bottom left-hand side. City 1, City 2, the air over City 1 is colder, and so it is contracted, and the height is lower. The air over City 2 is warmer, it's expanded. So if we take a point just below the top of the column, we see that there are fewer air molecules over that point in City 1 and more air molecules over that point in City 2. And so you have low pressure aloft in the colder air over City 1 and high pressure aloft in the warmer air over City 2, creating a pressure gradient in which air molecules move from column 1 to column 2. As those air molecules are evacuated or taken out of column 1 and they fill up in column 2 and they fill up in column 1, it increases the pressure at the surface in column 1, City 1, and as those molecules are moved away from high pressure aloft in column 2, it decreases the pressure at the surface. So at the surface, there's a pressure gradient from high to low, and the wind blows at the surface. The pressure gradient force is not the only reason that the wind blows. There's actually 5 forces that affect the horizontal movement of air or wind: the pressure gradient force, the Coriolis force, the centripetal force, the force of friction, and the force of gravity. The pressure gradient force being the movement of air from high pressure to low pressure, the Coriolis force being the apparent force due to the rotation of the Earth in the northern hemisphere, that is the deflection to the right. Centripetal force is an inward moving force in curved flow. The force of friction is when the wind interacts with objects on the Earth's surface to typically slow it down. And gravity is the force of gravity, which is a force of acceleration. Gravity is acceleration. It's 9.8 meters per second squared. Here is our look at pressure gradient force. The illustration on the upper right shows a straightforward view with high pressure to the left, low pressure to the right, and straight isobars between the two at about 1,000 kilometers apart. So the pressure gradient is the difference in pressure from point 1 to point 2, so 1,020 millibars minus 1,016 millibars. The difference in pressure, about 4 millibars, divided by 100 kilometers. That would be the pressure gradient. The pressure gradient force is the force from high pressure to low pressure. It is the difference in pressure divided by distance. That is the pressure gradient. The pressure gradient force is directed from higher to lower pressure, and that force is at right angles to the isobars. Our red arrow showing the net force from high pressure to low pressure is at a right angle to the isobars. The magnitude or the strength of that force is directly related to the pressure gradient, meaning in our illustration, it was 4 millibars over 100 kilometers. If we wanted to increase that force, we would either increase the number of millibars or shorten the distance. That would, either one of those would make that number higher. So to increase the pressure gradient, you increase the force of the wind. So isobars that are more tightly packed together create windier weather. Isobars that are further apart less wind. The horizontal pressure gradient is responsible for causing air to move. It is the single most important and the primary force in the wind, the horizontal pressure gradient, responsible for causing air to move. The PGF is the force that causes the wind to blow. Now, on a more typical surface map in the lower left, we have a big dome of high pressure somewhere above 1,024 millibars, and then isobars of 1,024 to 1,020 to 1,016. And the pressure gradient force, which is being shown at right angles to the isobars, and the magnitude of those red arrows is a function of the actual pressure gradient. In the lower left and the upper left, both of those arrows are long because we have a greater pressure gradient and we have a higher pressure gradient, a greater drop in pressure over a narrower distance. As you go around to the right side of the circle, the isobars are further apart. You have the same change in pressure, but over a greater distance, and the pressure gradient is lower. And this is what it would look like with low pressure at the surface on a more typical surface weather map. In the upper left, we have a deep low, lower than 972 millibars, right there over Iowa. Cold front, warm front, your area of low pressure. That's your typical mid-latitude cyclone or extratropical cyclone. Extratropical because it's out of the tropics. A very typical cyclone. And that point from X to X is where you have the greatest change in pressure from, it looks like 1,008 millibars to 972 over the shortest distance. And you can also see there the winds are blowing the fastest. Again, our wind barbs with each flag indicating 10 knots or 10 miles per hour. Right in that area across that green line, that's where the winds are blowing at about 40 to almost 45, about 40 miles per hour in that area, about 45 statute miles, but about 40 miles per hour. That's where the winds are the fastest because that's where the pressure gradient is the highest because you have the highest change in pressure over the shortest distance. You get down over Tennessee, we get down to 15 mile per hour winds. A little bit further north between Illinois and Indiana, we can see the winds increase to about 25 miles per hour because the pressure gradient tightens. And then we look at the lower right-hand side, and this is a tropical cyclone. So we're out in an area of low pressure without any frontal boundaries, and it's down around 943 millibars. And the winds around the surface, and of course they're blowing counterclockwise, have increased over the water to as much as 55 to 60 miles per hour, where over land, because that force of friction, the wind speeds are lower. But you can see where the pressure gradient is highest, you have the highest change in pressure over the shortest distance. That's where we have the highest wind speeds. The pressure gradient force is the force that causes the wind to blow. The next force that affects the wind is the Coriolis Force. This is an apparent force. The Coriolis Force causes the wind to deflect to the right of its intended path in the northern hemisphere and to the left of its intended path in the southern hemisphere. Objects moving in any direction are deflected depending on the rotation of the Earth. How fast the Earth is rotating will change the deflection. Of course, the Earth rotates at a steady rate, although it is thought that that speed is changing over great time periods. The second thing is the latitude of the object. At the equator, there is no deflection whatsoever. But the further north or the further south from the equator, the greater that deflection. And the deflection is also dependent on the speed. A very slow-moving object is deflected very little, where the faster the object speed, the greater the deflection. So, the greater the wind speed, in the case of wind, the greater the deflection to the right in the northern hemisphere. And the Coriolis force increases for all wind speeds from a value of 0 at the equator to its maximum at the poles. And the Coriolis force acts at right angles to the wind, only influencing the wind direction, but never the wind speed. So if the wind is blowing due north, from south to north, it's a south wind blowing due north, the Coriolis force is acting at a right angle to the right, so it's pulling it to the east. So we'll want to pull that wind to the east.
The Coriolis force is an apparent force that causes moving objects to appear to bend away from their intended paths. This force can be due to a rotating Earth, or in this example, a rotating platform. On a non-rotating platform, we can see that a thrown ball moves in a straight path to the receiver. Suppose the platform begins to rotate counterclockwise, just as the Earth rotates counterclockwise when viewed from above the North Pole. On the screen to the left, we see that the thrown ball moves in a straight line path. However, when we view the thrown ball on the rotating platform, the screen on the right, the camera reveals that because the platform is rotating, the ball in flight appears to curve to its right, and the receiver has to lean to the side in order to attempt to catch it. Even though the ball actually moves in a straight line, people sitting on the rotating platform see the ball appear to bend to the right of its intended path. The apparent bending of the thrown ball is due to the fact that the platform is rotating. The apparent force that causes the bending is the Coriolis force.
What happens then when we add the pressure gradient force to Coriolis force? What results in the level above the surface is a straight line wind. The straight line wind is also known as a geostrophic wind. It's the combination of pressure gradient and Coriolis. So if we are above the Earth's frictional force, so the force of friction between the ground and the trees and the buildings, we're above that level. A parcel of air at position 1, look at the illustration, position 1, is going to accelerate north due to the pressure gradient force. High pressure to the south, low pressure to the north. And again, the pressure gradient force is at right angles to the isobars. You see the isobars of 908, 904, 900. So the pressure gradient force is and remains from south to north at right angles to those isobars. The Coriolis force, once the parcel begins to move, begins to deflect the parcel to the right with increasing magnitude, increasing strength as that parcel accelerates. So at the point when the pressure gradient force and the Coriolis force become equal, the net forces between them become zero, and the wind flows in a straight path parallel to the isobars at a constant speed. So at position 1, the parcel begins to accelerate north. As it begins to move and as the parcel increases in speed, the Coriolis force increases in magnitude or in strength at a right angle to the wind direction. So it pulls it a little bit to the right to position 2, and you can see that the Coriolis force is a short blue arrow. The red arrow of the pressure gradient force remains the same because the pressure gradient doesn't change. And then as that parcel continues to be pulled to the left, to the right, the Coriolis force increases as the wind speed increases until ultimately at position 5, the Coriolis force is due south, the pressure gradient force is due north. Those forces cancel each other out and the wind blows at a straight line between the isobars. Evenly spaced and straight isobars, as you see in this illustration, do not exist in the atmosphere. So the geostrophic wind is simply an approximation.
So this is what it looks like when we add the pressure gradient force and the Coriolis force to end up with the straight line wind in the upper levels of the atmosphere.
The wind blows due to horizontal differences in air pressure. An air parcel, initially at rest and above the frictional influence of the surface, will begin to move from a region of higher pressure toward a region of lower pressure due to the pressure gradient force. Once the air begins to move, the Coriolis force in the northern hemisphere bends the moving air to the right of its path until the Coriolis force balances the pressure gradient force. At this point, the wind flows parallel to the straight line isobars or contours and is called a geostrophic wind.
If the geostrophic wind is a straight line wind aloft in the upper levels of the atmosphere that doesn't exist, then what must exist is curved winds, and that's exactly right. With a counterclockwise curving wind, as you can see on the left, being a cyclonic flow, a cyclone, and a clockwise curving wind, as you see on the right, being an anticyclone or an anticyclonic flow. Low pressure is a cyclone, high pressure is an anticyclone. And the reason why you get counterclockwise or clockwise is simply the fact that around an area of low pressure, the pressure gradient force increases and becomes greater than the Coriolis force, and so the air is pulled in and to the left. Whereas around an anticyclone or the high pressure, the pressure gradient force is less than the Coriolis force. The deflection to the right is greater, and it turns the wind to the right. So a gradient wind is a wind that blows at a constant speed parallel to curved isobars above the level of frictional influence. And again, cyclones and anticyclones. Centripetal force is that inward moving force. It's the PGF force with the low pressure and the Coriolis force with the high pressure. Centripetal force is inward moving. Any motion in a curved path represents accelerated motion, meaning if an object is moving along in a straight path at a constant speed, if it turns to the right or left or up or down, any motion in a curved is considered acceleration. That curved motion or that acceleration requires a force directed toward the center of the curvature to cause that curve to happen. This force is called a centripetal force, which means a center-seeking force. That force has a magnitude of m times v squared, velocity divided by the radius of the curve. The centripetal force is proportional to the square of the velocity, implying that a doubling of speed will require 4 times the centripetal force to keep the motion in a circle. And think about that. If you're going around a turn in a car, what is the centripetal force? It's the force that's keeping the car going around the curve. In this case, it's literally the tires being in contact with the asphalt. That's the force allowing the car to go around that curve. If you double your speed, you're far more likely to slide off the road and into the ditch because the centripetal force has to be 4 times greater to hold that car on that curved path. Anytime the word centrifugal or centrifugal, which is how scientists are saying it now, is used, what's really being described is a lack of centripetal force. So centrifugal force is that outward moving force. If something is moving in a circle, the outward motion is the centrifugal force, referring to a lack of centripetal force. A centrifugal force is apparent. It's also equal to the magnitude of the centripetal force, but directed outward. And there's a great illustration at this website that you see in blue or yellow. Go ahead and click on it, and it's going to show you a car going around a curve. Okay, so the car has centripetal force. It's being held to the road by the tires. But the tape deck, you've probably never seen an 8-track, maybe a cassette tape, sitting on the plastic dashboard. There's no friction between the tape. It's plastic, the dashboard's plastic. There is no force that holds that tape in. So as you go around the curve, what happens to the tape on the dashboard? Well, it slides out to the right. It slides to the other side of the car. If you look at this illustration, you actually see the tape is moving in a straight line. The car is in a curved path, and the tape is actually moving in a straight line. The car does have centripetal force and inward center-seeking force. The tires pulling it around the curve. The tape deck has no center-seeking force, so it has centrifugal force and gets pulled out. How does that play out in the atmosphere? We can see it at work on the winds on an upper level chart. So we're no longer looking at a surface chart. If you look at the bottom left-hand corner of this illustration, you see 500 millibars. And what we're looking at is where 500 millibars exists everywhere across the Pacific, Atlantic, Gulf, and the continental United States, Canada, and Mexico. We know that in warmer air, the column of air is higher, and in cooler air, the column of air is lower. We see our high over the Yucatan Peninsula and the low over Oregon, where up north it's going to be colder. Now, if you look at those red dotted lines, those red dotted lines are isotherms, and they're telling us the temperature at 500 millibars. 10 degrees below 0 Celsius over the southern parts of the country, 15, 20, and then in that low across the Pacific Northwest, the temperatures at 500 millibars are 25 below 0 Celsius. So if you look at the right-hand side of this illustration, along the lines, instead of those lines, those contour lines being in millibars, in our upper level charts, those contour lines are literally showing us the height in meters above the surface. So if you look at the high, just off the Yucatan, right over the Yucatan Channel, it looks like Cuba is missing, that high is telling us that 500 millibars is found at 5,880 meters above the surface, where our low over Oregon is found somewhere around 5,660 meters above the surface. So the high over the Yucatan, the 500 millibar level, is higher because the air is warmer, it is thicker. The low over the Pacific Northwest, that 500 millibar, is lower because the column of air there is contracted because it's colder. So those contour lines showing heights above the surface, those become our curved contours. And you can see that the winds in these curved contours are blowing essentially parallel to the contours with the greatest speeds where there's the tightest pressure gradient over the Pacific Ocean. There is a high just off of California and the low over Oregon. So there's a nice tight pressure gradient, and that's where your wind speeds are highest. Whereas over Florida in the Gulf of Mexico, there is a much lower pressure gradient, less of a change in pressure over distance, and the wind speeds are much lower. But again, in the upper level chart, those winds are blowing parallel to the contour lines. If you go back in this lecture to the surface charts that I showed you over the United States and over the ocean, you'll see that the winds don't blow parallel at the surface. They cross the isobars. They cross the isobars out of high pressure into low pressure, and that's because of the force of friction, and we'll show you that in a moment. So gradients in contour lines, the tighter the gradient, the faster the wind speed. Now, where those contour lines are due north and south, as you see over the Pacific Ocean, we call that a meridional wind or a meridional flow because it's following the meridians, the lines of longitude. That's a north to south or a south to north trajectory. Where the winds are more west to east, that's considered a zonal flow. And these height contours on upper level charts are interpreted in the exact same way as isobars are on surface charts. So let me draw your attention to the high and the low over the Pacific and the Pacific Northwest. What is the pressure gradient force? The pressure gradient force is from high pressure to low pressure, so from west to east. What does the Coriolis force do? Without the force of friction, it turns it to the right. And you can see that those winds are turned to the right and blowing from north to south. Now, the same thing can be said with our high pressure over the Yucatan compared to the low pressure over the Pacific Northwest. The pressure gradient is from the southeast to the northwest, but again, Coriolis turns those winds to the right, and the winds blow parallel to the contour lines. So the map that we're just looking at would be known as an isobaric map. Iso meaning the same, baric referring to pressure, where every surface on that map is the same atmospheric pressure. And in the case of the upper level charts we'll look at, that will be 500 millibar charts or 500 millibar maps. An isobaric map depicts points in the atmosphere of equal barometric pressure. The points are depicted as the number of meters above ground level of a constant pressure surface of 500 millibars. The height of that constant pressure surface is known as the thickness. So, in this illustration to the south, the air is warmer and that 500 millibar level is higher. It's 5,700 meters plus up in the atmosphere. It's a higher height. It's a thicker atmosphere. Where, to the north, where the air is colder, that 500 millibar level is at 5,580 meters. 5,700 meters in the warm air, 5,580 meters in the cold air. And so it creates a gradient, a downslope from high pressure to low pressure. And of course, the Coriolis force would turn those winds, that gradient to the right, and the winds would blow parallel to those contour lines. So contour lines show us the thickness of the atmosphere or the height of the atmosphere. Thickness is directly proportional to the average temperature of the layer. On isobaric maps, constant pressure maps, also known as thickness maps, or sometimes even maps of average temperature, the thickness is directly proportional to the temperature, with thicker areas, higher heights being over warm, and lower heights over cold. So the height lines illustrate pressure in the same way as isobars and winds, and they'll also show how wind will blow from high pressure to low pressure. With higher heights and thicker atmosphere, the air is warm, and lower heights and less thick atmosphere where the air is cold. This is another interpretation of the isobaric map. You're looking at the surface, or looking at the bottom of this illustration, the brown, yellowish brown area, we see our curved contour line. So again, this is at 500 millibars, so this is a loft, not at the surface, this is a loft. And those curves showing the ridge of high pressure to the west and the trough of low pressure to the east. And again, in the high pressure, in the upper levels, high pressure associated with warmer air, and that atmosphere there is thicker. And in the low pressure to the east is associated with colder air, and that atmosphere is less thick. And again, creating the pressure gradient from warm air to cold. In this figure, the thickness of the atmosphere is represented above the isobaric map. A ridge of high pressure in the upper levels of the atmosphere is associated with warmer air and higher heights, thicker thickness. A trough of low pressure in the upper levels of the atmosphere is associated with colder air and lower heights, less thickness. Air in the upper levels moves from high pressure to low pressure, deflected to the right by Coriolis along those constant pressure lines. And those constant pressure lines, 5,640 meters, 5,580 meters, 5,520 meters, those are heights above ground level in meters, and those constant pressure lines are height lines or thickness lines. This is how the upper level winds blow. Warm air at the equator is associated with high pressure in the upper levels of the atmosphere. Cold air at the poles is associated with low pressure in the upper levels of the atmosphere. Due to the pressure gradient force, air blows from high to low pressure and is deflected to the right in the northern hemisphere and to the left in the southern hemisphere. This results in the westerly winds that prevail over the mid-latitudes in the upper levels of the atmosphere. What happens when we add the force of friction and we get our wind at the surface? So these three illustrations, we see the wind aloft. Of course, on the left, the pressure gradient force is equal to the Coriolis force, and we have a straight line geostrophic wind that blows parallel to the straight isobars. What we know really happens with the centripetal force is that winds blow counterclockwise around low pressure and then clockwise around high pressure. So counterclockwise around troughs of low pressure in the upper levels of the atmosphere, and then clockwise around ridges of high pressure in the upper levels of the atmosphere. But what does happen when you get down there at the surface and you add the force of friction? Well, now we get a lot of complicated vectors. The first two, or at least the first one, is going to be the same. On the left-hand column, the pressure gradient force remains the same. So initially that wind begins to blow in that straight line between those two isobars. But what does the force of friction do? It slows down the wind. With slower winds, what other force is reduced? The Coriolis force. Remember, the magnitude of Coriolis is dependent on wind speed. So at slower wind speeds, there's less Coriolis force, which means the deflection to the right that caused those winds to blow parallel to the isobars is lower, and the deflection to the right is less. So that purple line, because of the force of friction, green, that purple line with a slower moving wind, you can see that purple line at the surface is shorter than the purple line aloft because friction's caused it to slow down. That surface wind is not blowing quite parallel, but has been deflected not quite so far to the right and is more to the left, and it's literally blowing out of high pressure into low pressure. The planetary boundary layer is the atmospheric layer that is influenced by friction, usually up to about 1,000 meters or 3,000 feet. At low elevations, friction will slow the air, and hence the Coriolis force will be less in its deflection of the wind. With height, the effects of friction are lessened, and the wind blows faster in parallel to the contour lines. Here is another illustration of how the force of friction affects surface winds. Again, A, the upper level wind, no friction. The Coriolis force and the pressure gradient force are in equilibrium. The net is zero, and the wind blows parallel to to the contour lines, a nice long purple line with a fast-moving wind. Down at the surface, the pressure gradient force is the same, but the force of friction has slowed the air. The slower moving air means the Coriolis force is shorter. Both of those arrows are shorter than what's happening aloft. The purple arrow and the Coriolis arrow, both shorter, which means the wind is not deflected as far to the right and actually moves out of high pressure into low pressure. The wind aloft is blowing above the planetary boundary layer and above the level of frictional influence of the ground. At this level, the wind is approximately geostrophic, blowing parallel to the contour lines with the pressure gradient force and the Coriolis force in balance. The surface wind is slower due to the drag of friction. The reduction in wind speed reduces the Coriolis force and the deflection to the right is lessened. The resulting wind blows across the isobars, important, across the isobars, out of high pressure and into low pressure. The pressure gradient force here is now in balance with the force of friction and Coriolis. Of course, in the northern hemisphere, winds moving counterclockwise into low pressure and clockwise into high pressure. Here we can line the two charts up with a surface chart on the left and an upper level, upper air, or a 500 millibar isobaric chart on the right. At the surface, you can see how the winds blow across the isobars, out of high pressure and then into low pressure, whereas in the upper air chart, the 500 millibar chart, those winds, the purple lines, blow essentially parallel to the curved contour lines, those contour lines showing the height in meters above the ground level of the 500 millibar surface, with higher heights or a thicker atmosphere to the south where it's warm, and lower heights or a colder atmosphere to the north where it's cooler. And again, the pressure gradient force from that high over Louisiana is directly toward the low over Canada and directly toward the low over Maine. It's the force of Coriolis that turns it to the right, the winds to the right, and causes them to blow parallel to the contour lines. So surface maps are lines of equal pressure. High pressure is an anticyclone, and low pressure either a mid-latitude cyclone or an extratropical cyclone. Sometimes out over the ocean, they would be tropical cyclones. Because of friction, the wind blows across isobars in toward low pressure and out of high pressure. On isobaric maps, or constant pressure maps, or thickness maps, all the same thing, contour lines are lines of equal elevation, with low height meaning low pressure or cold air, and high height meaning high pressure and warm air. Ridges and troughs. The red dashed lines, those are your isotherms, or lines of equal temperature, at 500 millibars. And again, the winds blow parallel to the contour lines. The most important thing to understand when comparing upper level charts and surface charts is that they are connected. And upper levels of the atmosphere and the surface are connected by rising air and sinking air. And we know that sinking air at the surface creates high pressure and rising air at the surface creates low pressure. So what's happening in the upper levels with regards to divergence, air diverging from a center of high pressure, or with regards to convergence, air converging into a center of low pressure, what's happening in the upper levels forces what's happening at the surface, where divergence aloft, air cannot be pulled down from above the tropopause, so it has to be pulled up from the surface, creating rising air and convergence at the surface in foul weather, with the converse being convergence aloft. Again, air is converging aloft. It cannot go up to the tropopause, so it's forced to sink, creating high pressure, divergence at the surface, and fair weather. Nice illustration of this whole concept in the animation on the next slide. All right, once again, if you have to click to get this started, go ahead and do so. What you're seeing is a zonal flow in the atmosphere becoming more meridional and a trough of low pressure forming in the atmosphere. On the entry level, or the entry side of that trough, air is converging, and in the exit region, air is diverging. So in the entrance region, air is coming together or converging. In the exit region to the right of the low, air is spreading apart or diverging. So there's your convergence in the upper levels and divergence in the upper levels. Well, the convergence in the upper levels causes that air to sink and high pressure forms at the surface. In the same way, in the exit quadrant or exit section of this trough, divergence aloft pulls air up off the surface, and rising air creates convergence, and of course, rising air, low pressure, convergence, that's where we get our foul weather. Now that low, as it begins to spin, pulls cold air in from the north, on the back side of the low, the west side of the low, warm air in from the south to the east of the low. There are your showers and your thunderstorms that are associated with it. But with that cold air being pulled south, a cold front forms south of the low, and a warm front forms to the east of the low, and the low follows the wind in the upper levels of the atmosphere. That low gets moved along off to the north and east, and that's how our mid-latitude cyclone travels. So once again, winds in the upper levels of the atmosphere are connected to winds in the lower levels of the atmosphere by those vertical motions.
All right, that was Chapter 6, Air Pressure and Winds. Coming up with Chapter 7, we'll be talking about atmospheric circulations and the different scales of atmospheric circulations and what types of winds we find at those different scales.